Alright, so in this video I'm going to take a look at the January 2011 Unit 2 paper on mechanics, materials and waves. So we're looking at first at an exercise device to provide resistive forces. Exercise devices seem to come up quite a lot in these Unit 2 papers, but they've got some good stuff about springs and things, so I guess it makes sense. So essentially what we're going to do is look at compressing the spring. So that's what we're going to do, so like squashing it together. Okay, so the force exerted by the spring over a range of compressions was measured and the results are plotted, and it's a spring, so surprise, surprise, the force versus a delta L graph is a straight line through the origin. Okay, so let's have a look at some of the questions. All right, so first, a classic spring type question, state Hooke's law. So Hooke's law states that force is directly proportional to the change in length or the compression or the extension up to the limit of proportionality. So let's get that down. So that's what we've got here. So moving on to the next one, state which two features of the graph confirm the spring obeys Hooke's law. So to be directly proportional, you need to be a straight line graph through the origin. So those are the two features. Okay, so we've got that. So then it wants us to use the graph to calculate the spring constant. So what we're going to need to do is determine the gradient of the line. So what we're going to do is I'm going to flip back and pick up some values from the graph. Okay, so quite a nice point that it goes to is 0.28, 360. So I'm going to use that point as one of the coordinates and 0, 0 is the other. So the gradient is going to be change in y, so 360 minus 0. We have a change in x, so 0.28. minus 0, and that gives us a gradient of that's 1285, so that's going to be 1.3 times 10 to the 3 newtons per meter. To two significant figures, which would seem appropriate given that all your x values are two significant figures there. So that is your spring constant. Alright, so the formula for an energy stored in a spring is half F delta L. Explain how this formula can be derived from a graph of force against extension. So the first thing is that the work done on the spring, or the energy stored in the spring, is the area under a force versus extension graph. And the area is a triangle, so the area is half base times height. Therefore, that's where the equation comes from. So let's put that down into words on text. Alright, so I've broken it into three colours based on what I think the three marks will be. So the first thing is that the area under a force versus change in length graph is the work done to change that length. A lot of people think that the area under the graph is equal to the energy stored. That's not quite correct. So it's essentially area under a force versus displacement graph is work done. And then if we assume all of the work is transferred into stored energy, that's when we equate it to stored energy, but very often there'll be some waste in causing permanent deformations, those kind of things. So then the final one is, well, the area is a triangle, so its area is half base times height, and that's where this equation comes from. Okay, so that's that one there. So let's continue on. So the person causes a compression of 0.28 meters in a time of 1.5 seconds. Use the graph to calculate the average power. So first, let's work out the energy or the work done. So handily enough, this is the point I picked up in the last question. So we already know what the force is. It was 360. So this represents the work done, which is about 50.4. Power is the rate at which work is done, so the average power would just be your work divided by the time at which it happened, so 50.4 divided by 1.5, giving us a value of 33.6, so that's going to be 34 watts to 2 SF, which would be appropriate. Alright, so that finishes the materials and a little bit of energy. Next, it looks like we're going to see some projectile motion. Oh, very exciting. We've got defeating enemy ships with cannonballs, always good. So we've got a castle overlooking a river. A cannon fires at the ships, and it looks like they're fired horizontally initially, and it travels a horizontal distance of 150 meters when the vertical distance is 67, and it is indeed fired horizontally. Show that the time taken for a cannonball to reach water surface after being fired was 3.7 seconds, assuming no air resistance. So the thing to realize here is that flight time only depends on vertical components of velocity. The horizontal have no effect on flight time at all. So then we also know its initial vertical velocity is 0 because it's traveling horizontally, and it's accelerating under gravity, so that should be all we need. So let's get that key information down. Okay, so when I'm doing these motion type things, I like to pick out from the question what I've got and write it out like this. So we can see it's falling downwards 67 meters, so that's why the displacement's minus 67. The acceleration is downwards, so we've got an acceleration of minus 9.81. We don't know what its final velocity is, so we want the equation without v in it, and we want to solve for t. So the equation that doesn't have v in it is this one, so s equals ut plus half at squared. U is 0, so we can immediately get rid of that term. So we can get the time is going to be 2s over a square rooted. We're not going to be interested in the negative square root here, so that's why I haven't written positive or minus, because we're never going to get minus times. That's 2 times by minus 67 divided by minus 9.81 square rooted, and if we do that we end up with 3.696 yada yada yada, which is roughly 3.7 seconds there. So you may well have got plus 67 and plus 9.81. If you're using the downward as the positive direction, that's fine too. You see in this equation the signs will cancel out anyway, because these two S and A will always have the same sign whichever way you use direction, so that will be fine to do. But just an FYI. Other quick thing, in the real exam, do not write outside these lines. Nothing outside these lines gets scanned in, so it doesn't matter what you write, the person marking it's not going to see it because it's not scanned onto their computer, so do watch out for that. Okay, so that's 2A part 1. So calculate the velocity at which the cannonball was fired. So we've got the flight time, and we know the distance in the horizontal direction it travels, that was 150 meters, and we also know the velocity is constant in the horizontal direction because there's no horizontal forces acting. So what we can do is we can use the equation v is s over t. Because velocity is constant, we can use this very basic form. We know it's 150 meters in the horizontal direction, and we know its initial velocity was in the horizontal direction. We know the time is 3.696 yada yada yada, giving us a velocity of 41 meters per second. To 2 significant figures would be appropriate there, because the value this 3.696 come from are 2 significant figure values, so that's why we would do that. So in the previous part of the question, when we calculated the time, those are based on 2 SF values, like the 67 meters, so that's why. Okay, so calculate the vertical component of velocity just before it hits the ship. So the equation we're going to want to use a t. We know u is 0, so it's just going to be minus 9.81 times by 3.696. So then that's going to end up being minus 36 meters per second, or 36 downwards with a positive number. Either of those would be fine depending on which you used as the positive direction. So let's just indicate for the examiner that I'm using that direction as negative. Then it's very clear what I'm doing. By calculation or scale drawing, find the magnitude and direction of the velocity of the cannonball just before it hit the ship. So we've got two components. We've got the horizontal, now we've got the vertical. So this is minus 36. This one is 41. So the resultant is going to be that direction. So I'm going to calculate this angle in here. So theta is going to be found using the inverse tan function, which is opposite over the adjacent. And if we calculate that, it comes out as 40. Well, I use the unrounded versions actually, so it comes out as 42. It's minus 42 degrees, or 42 degrees below horizontal. So that's your angle. We're going to find the resultant using some Pythagoras. So let's call the resultant r. So r is the square root of 31 squared. We don't need the minus sign anymore because it's 36, isn't it? So it's 41. I'm actually using the unrounded values, but it's quicker to write out these ones. And that's going to come out as 54 meters per second to 2SF there. Okay, I would never recommend doing these by scale drawings. One, it takes a lot longer and you're more likely to make mistakes with it, but enjoy if you like drawing. Calculate the loss in GPE of the cannonball. So we know the change in GPE is mg delta h. So that's 22 times 9.81 times by minus 67. That's the change in GPE. So that's 14460, or 1.4 times 10 to the 4 joules. So therefore the loss is 1.4 times 10 to the 4 joules, because loss potentially takes away that negative sign. Okay, so let's continue on. So to finish off, it wants us to describe the energy changes that take place from the moment the cannonball leaves the cannon until just before it hits the water. So what's happening is the useful energy transfer is GP to kinetic energy to increase its velocity, but then you're also going to do some work against air resistance, turning GP or kinetic energy into thermal energy or heat. So let's get those two down. Alrighty, so that's what we've got there. Those are the two energy transfers, and those are where the two marks come from. Okay, so let's move on to question 3. So we're going to look at some single slit diffraction. So we're doing it with a laser, and we've got an intensity sketch. Sketch how intensity varies across the screen to the right of the central maximum. So the first thing to remember about single slit is the central one is double the width of all the others. So for each one, this is now going to be 1, 2, 3 maxima drawn there, and they should be decreasing in the maximum height or amplitude, if you like to call it that. So let's just have a go at this. So next one will be like this. Next one will be like this, and then the next one will be even lower, like this. And that's what it's going to be looking for the sketch. So the two things they'll be looking for is decreasing maximum and that they're all half the width of the central one. Those are the two marks. A laser is a source of monochromatic coherent light. State what is meant by monochromatic and coherent. I swear this was on last year's exam. Well, they were very nice to this year group, clearly. But let's get those down. So monochromatic is light of one wavelength. Coherent is when the light has a fixed phase difference. So that's what we've got there. Those are your two definitions. So let's move on to the next part. Okay, so describe how the pattern would change if a light of a longer wavelength was used. So we have, for a single slit, we have an equation for the width of the central fringe is 2d lambda over s, where s is the size of the central slit. So we can see there, if we use a longer wavelength but keep distance and slit size the same, that the central fringe is going to become a lot wider, and that's going to make all of the other maxima wider as well. Okay. All right, so that's, we just need to describe, we don't need to explain stuff like looking at the relationship, but I find the equation helps me figure out what's going on. State two ways in which the appearance of the fringes would change if the slit was made narrower. So the first thing is that fewer photons would be able to get through, so the intensity of your peaks would be smaller. And you can also see from the equation above that if we make this number smaller, the fringes will become wider. So those are the two things, and therefore the two marks. Alrighty, so let's continue on. So the laser is replaced with a lamp that produces a narrow beam of white light. Sketch and label the appearances of the fringes as you would see them on the screen. So I'm going to draw what you would see with, so this, let's say this is your the center of your screen. So red light has a longer wavelength, so you'd expect all of the fringes to have red on the outside, and then they would have violet on the inside, but the central one would be white. So let's sketch. So let's say this is your double width. Oh, blimey. So this is your double width central one, which is white there. And then with the next fringe out, it's going to be violet coloured on inside, and it's going to be a little fatter than half of the central one because it's spread out with two wavelengths, and then you get the full spectrum in between. And then what you get further out is actually these start splitting up into full-on separate fringes the further out you get. So let's start showing that. And then we get a symmetrical pattern on the other side. Oh, whoops. That one should be violet. Violet there, red there, and then you start getting, oh, I've done it again. You actually start spreading out into separate fringes as you get outward on the pattern. So this is basically what it's looking for. So then, just to label a few things in here, as you go across, there's a full spectrum. And what I'm showing here is the fringes separate. So instead of having a fringe that goes from violet to red, what you get is a violet, green, orange, yellow, like all red separate fringes as you get further out. So those are the things you would need to be showing. In terms of where the marks are for here, so the first one I think would be for having a double width white central fringe. The next one would be for having the next fringes out have violet on the inside, red on the outside, and a full spectrum in between. And the last one would be for those who recognize towards the outer, the fringes actually separate out into split up ones. That's what I think the marks will be for there in this question, but generally only the best candidates would recognize that this happens on the outside, so that's how you distinguish yourself there. Okay, so that finishes the interference question. Alrighty, so we're going to look at some stationary waves. So you've got it's fixed at one end, that's on this one where it's clamped over here and forced to be a node here, and we've got it oscillating on this side at A, and we're going to oscillate it at a fixed frequency. So we're going to do a longer answer question, explain how a stationary wave is formed, and describe the key features of a stationary wave. So essentially I'm going to break this down into three parts. So the three key features of a stationary wave are that it forms nodes, points of zero displacement, antinodes, points of maximum displacement, and that there's no energy transfer in it. And we're going to explain how each of those things are formed. So let's first get the general criteria for making a stationary wave, and then describe how each of the features are formed. Alright, so the starting point is to make a stationary wave, you need two progressive waves that meet each other. So they need to be traveling in opposite directions at the same speed, and they should also have the same wavelength or frequency and a similar amplitude. Those are the general criteria that form a stationary wave. So let's now start looking at the features of the wave. So let's talk about nodes first of all. Okay, so nodes are points where there is no displacement from the equilibrium position. They're formed where the two progressive meets in antiphase. A lot of people drop marks here because they just say out of phase. No, you need to be specific. It's antiphase or 180 degrees out of phase. And what happens then is destructive superposition occurs because a peak meets a trough. So that's why nodes are formed. Let's now talk about antinodes. So our antinodes are points of maximum displacement or maximum amplitude, and they're formed where the two progressive waves meet in phase or with a phase difference of 0 and constructive interference occurs. The final thing to talk about is the fact that there's no energy transfer, and that's because the two superposing waves have the same speed as each other, so there's no net energy transfer, because essentially the energy one's transferring one way is cancelled out by the energy transferred the other way. So let's finish off with that. So that's the final stage, and that's the third and final feature I would look at here. With regards to this wave we're looking at here, we could have been more specific, so actually we formed 3 antinodes and 4 nodes. For this wave you could have talked about the fact the wavelength is 0.8 meters, because that would be specific to this one being shown, but what I've done should be a good answer for any kind of stationary waves question, but those you could add in to be a bit more specific for this particular wave here. Okay, so that finishes that question on stationary waves. Okay, so we've got during the moon landing, the lunar module separated from the command module above the surface of the moon when it was traveling at a horizontal speed of 2040 meters per second. To descend, it needed to reduce its speed using its rocket. So you can see that the rocket is firing in the opposite direction to the motion, so it's going to act to slow it down. The average thrust from the rocket was 30 kilonewtons, and the mass of the lunar module was 15,100. Calculate the horizontal deceleration of the lunar module. So we're going to need to be applying Newton's second law, a simplified version of it, which means we need to divide the resultant force by the mass. So if we were calculating acceleration, we would put minus 30,000 here. Because we want deceleration, we can just put 30,000 in here. Mass is annoyingly not quite 15,000. That would have been nice. But what are you going to do? So this comes out as 1.99. So to two significant figures, which would be appropriate, it would be 2 meters per second squared. Okay, so calculate the time for the lunar module to slow to the required horizontal velocity of 150 meters per second. So we, as usual, this is going to be a motion type or SUVAC question, so let's get the key things. So that's what we've got there. So the thing we don't know is displacement, so we want the equation without displacement, and we want time. The equation without displacement is V equals U plus AT. So to get T, we need V minus U over A. So that's 150 minus 2040 divided by an acceleration of -2 because it's against the motion. Now we put those numbers in, we get a value of, I think it's 950 odd, or as to two significant figures, 9.5 times 10 to the 2 seconds. Okay, so let's carry on. Okay, so once we've slowed down, the rocket was then used to control the velocity of descent. So it descended with constant velocity or acceleration of 0 or resultant force of 0. Due to the use of fuel during the previous deceleration, the mass has fallen by 53%. And the acceleration due to gravity is 1.61 meters per second squared. Draw force vectors to show the forces acting on lunar module at this time and label them. So we're going to have on here, we're going to have a weight force going from roughly the center of mass of the object, and then there's going to be a thrust force acting upwards to give you a resultant force of 0 to maintain a constant speed. Okay, so that's what we should have there. So calculate the thrust force needed to maintain constant downward vertical velocity. So I said thrust is equal to the weight force, which is equal to its current mass times the gravitational field strength of the moon. So that's, it said it was 53% of its original mass. Was it 15,100? And that's times by 1.61, because that's the acceleration due to gravity on the moon. And then when we do that, it comes out as like 11426, so 1.1 times 10 to the 4 newtons of force are required, which is about a third of what it was earlier, so that doesn't seem to be a problem. When the lunar module was 1.2 meters from the lunar surface, the rocket was switched off, and at this point the vertical velocity was 0.8 meters per second. Calculate the vertical velocity at which the lunar module reached the surface. So let's again write out our equations of motion, seeing as we've changed directions. Okay, so it's traveling downwards, so its displacement will be negative. Its initial velocity, actually, that's going to be minus 0.8 because it's in the downward direction. We don't know it. We want to know its final velocity. We know its acceleration. So let's work through. So we don't have time, so we need the equation without time in it. So that's going to be v squared equals u squared plus 2as. So v is going to be the square root of 0.80 squared, so we can see actually it wouldn't have mattered if we got the sign wrong for u in this case, but luckily we picked it up. 2 times minus 1.6 times by minus 1.2. So again, if we use the downward direction as positive, it would have made no difference because the two signs would cancel each other out. And when we calculate this, we end up with like 2.1222, so essentially 2.1 meters per second to 2SF. And that concludes question 5. Let's move on. All right, so we've got a cable card system used to transport people uphill. We've got a cable has a cross-sectional area of 2.5 times 10 to the minus 3. I sense some young modular stuff coming up if we've got cross-sectional area and stress, that kind of thing. So we've got a graph shown for a 10-meter length of the cable as we apply different loads to it. Draw a line of best fit. So we're going to have a straight line section initially, and then it's going to curve off smoothly towards the end, or at least that's what I'm hoping. Alright, so the 2 marks essentially for showing a straight line section to start off with, then show it curving off. It would have been better if it curved off slightly higher, but I'm afraid my drawing on this device isn't great, so that's probably the best I'm going to be able to do. But it should be smoothly going through all the points realistically. Use the graph to calculate the initial gradient of this sample of cable. So let's find a nice point on our graph. I reckon this point up here is pretty good. So I think that's 3.4 millimeters and 1.7 times 10 to the 5 newtons. So the gradient of the graph, we change in y, so that was 1.7 times 10 to the 5 divided by 3.4. 4 times 10 to the minus 3, which comes out as very nice 5.0 times 10 to the power of 7 newtons per meter to SF there. There'll be a range of values there. What I would also always do, which I haven't shown, is actually show what you're doing on your graph. So your triangle is essentially being formed here, and then you read off the values and then done the gradient. So that's where I'm showing the triangle. Alright, so the cable breaks when the extension reaches 7.0 millimeters. So you calculate the breaking stress, state, and appropriate unit. So if we read off from the graph, at that extension, the force is 2.8 times 10 to the 5 newtons. Stress is force divided by area. We were given the area right at the beginning of the question. So 2.8 times 10, if I divide, times 10 to the 5, divided by 2.5 times 10 to the minus 3, giving us an answer of 1.1 times 10 to the 8 newtons per meter squared, or you can give that as pascals if you want to. Those are the same thing. So in a cable car system, a 1,000 meter length of cable is used. Calculate the extension of a cable when its tension is 1,150 kilonewtons. Sorry. So if we want to get extension, we need F over K. This is not a graph, so we can't exactly read it off. So 101, and we got K earlier. It was 5.1 times 10 to the 7. When we do that, we should end up with, it's like 2.94 times 10 to the minus 3. So this would be your extension of a 10 meter cable. So the extension here is going to be 100 times that. Which is going to be 0.29 meters, so a 30 centimeter extension, which over 1,000 meters doesn't sound like a particularly large amount. So let's move on to the final question, question 7. I feel like we haven't had a refraction, and indeed we've got some refraction. So we've got a layer of oil floating on water inside a glass container. A ray of light in the oil is incident at an angle of 44 degrees on the water surface and refracts. We've got these refractive indices. Show that the angle of refraction is about 50 degrees, so it's going from oil to water. So we're going to use Snell's law here. Let's not discuss the fact he basically stole it from other people, but never mind. So we want theta 2, which is going to be the inverse sine of N1, so it's starting off in oil, and it's by sine of, what was it, 44? And it's going into water, so 1.33. When we put all of those in, we get 50.15 blah blah blah, so it's going to be 50 degrees to 2SF, which would be what we're looking for. So the oil and the glass have the same refractive index. Draw the path of the light ray after it strikes the boundary between water and glass and enters the glass. Okay. So first of all, if we're going from water to glass, it's going from low to high, so that can't be totally internally reflected. So we're going to see it bend back towards the normal in this case, and then go straight through the glass. So something like that, and that angle in there should be bending back that way, so that will be 44 degrees in there, because we can be precise, so we should, and we did ask for that anyway. So explain why TIR will not occur. So that's what I just spoke about. The fact is going from low to high optical density. So that's what we've got there. So TIR can only occur when it's going from high to low, so it's impossible. I don't know why we got so much space to write that. Seems fairly concise. Calculate the critical angle between the boundary between glass and air. So at the critical angle, the angle of refraction is 90, so sine of it is 1. So N1 sine theta critical is N2. So theta critical is the inverse sine of N2, which is it's going from N2 is going to be air, so that's going to be 1. It was going from glass, so that's 1.47. When we plug that in, it comes out as 43. Actually, no, we can give this to 3 significant figures, so it'd be 42.9 degrees. That looks like I've put an extra decimal place in there, which I really did not mean to do. That's 40. This one is meant to be 42.9 degrees. Okay, so on figure 8, complete the path of the ray after it strikes the boundary between the glass and the air. So annoyingly, I can't go back and sketch this, so I'm just going to describe what you would see. So the first thing you'd see is it reflecting back off of the boundary of the glassware with the angle of incidence equal to the angle of reflection. So that's the first thing you'd see. So That's one thing you would see it. Then you'd see it refract at the glass water boundary, bending away from the normal. There. And then you'd see it bend towards the normal at the water oil boundary, and then you would see it go straight through unchanged when it goes into the glass, because oil and glass have the same optical index, so you'd have no path change at the glass oil boundary, so it would just keep going straight on. So those are the points that you would make there. So that completes this question, and in fact completes this whole exam paper. So I hope you have found this useful. If you've spotted any mistakes or is anything that's not clear, please do comment and let me know so I can clear that up for you. Do check out my other playlists on Unit 1, 4, 5, which are all complete already for help with those exams. But thank you very much for taking the time to watch.